Welcome back everybody to another video lecture from Miss Semino. This evening we're going to be talking about stoichiometry. Of course there's going to be several different stoic videos that we look at. This first one we're going to be just introducing stoichiometry, discussing what it is, and then how to use chemical formulas in stoichiometry. The next video is going to go ahead and show you how to do those stoichiometry equations where you're converting from one substance, maybe grams of one substance, to another. Just a quick reminder, if you're in regular chem, this is going to be chapter 12 in your textbook, and if you're honors chem, this information is going to be found in chapter 9. So as I joked in the last slide, many people think that stoichiometry is really a scary topic, but it's really not. In fact, we use it in our everyday lives. So I just want you to think about this little in question here, this introductory question. So if you have pancake recipe and it calls for 2 cups of mix and 2/3 cups of milk to make 8 pancakes, how much of each ingredient will you need to make 40 pancakes? So this is all stoichiometry is. We're looking at our reactants, and then we're just trying to figure out for how many products. So how much of our ingredients do we need to make our final products? So I'm hoping that you're thinking about, well, how would I solve this? So I'm looking here between this number 8 and 40, and it looks like I could do like a little math and go times 5. 8 times 5 would give me 40. So all I need to do is just to multiply all of these ingredients amounts by 5 to get the total amount that I would need to make my 40 pancakes. Another thing that we do in stoichiometry is we figure out which ingredient is our limiting reagent. And I know right now you're thinking, oh my god, limiting reagent. But it's really just as simple as this other example problem. It says if you need to make 32 pancakes and you have 8 cups of mix and 3 cups of milk, which ingredient will you have an excess amount of? So excess means you're going to have too much of. The other ingredient would then be our limiting ingredient, and that's what I was just mentioning a second ago. So take a second and think about this. So again, you're probably thinking something similar to, okay, I have 32, I could initially make 8, this is a difference of 4, so then if I multiply my ingredients up here by 4, this would give me 8 cups of mix I would need, and then, you know, a certain amount of milk that I would need, and it looks like I'm going to have extra milk left over, and that would be our excess amount. That would then make the mix our limiting reagent. So just a quick reminder that stoichiometry can be challenging, but in an effort to make it as easy as possible, you're going to want to follow along with your book and your calculator each day in class. You're going to do better if you follow along with your book during lectures, so maybe you want to have your textbook out as you're watching this video. And then you want to make sure that you're doing the practice problems to be successful. This is a chapter that stoichiometry is a skill. You have to practice that skill to be good at it. So you're going to want to make sure that you're practicing by doing the practice problems. So our formal objectives in this first video is to explain how balanced equations apply to both chemistry and everyday life, and we sort of did that a little with our introductory questions. We also want to interpret balanced chemical equations in terms of moles, representative particles, mass, and gas volume. This is probably the most important objective that you're going to need for this video. Then we also want to identify the quantities that are always conserved in a chemical reaction. This is a good factoid thing for your test and for general understanding about what's going on in stoichiometry. Okay, so here's another introductory to get you thinking question, and it says, let's make cookies. So when baking cookies, a recipe is usually used telling the exact amounts of each ingredient. It's not a shock there. But what if you needed to make more than just the 24 cookies that you normally could produce with the set amount of ingredients? So if you need to make more, you can double or triple the amount, okay, of ingredients. Thus, a recipe is much like a balanced equation. So a recipe is like a balanced equation. So this scary word, stoichiometry, is just Greek for meaning that it's measuring elements, and you pronounce it stoichiometry. I know it's kind of a weird way to say that out. So the formal definition is a calculation of quantities in chemical reactions based on a balanced equation. So we've already talked about how to balance equations. So whenever you do a stoichiometry problem, it's very important that you start off with a balanced equation. Otherwise, your calculations are going to be incorrect. Now here's where we start to get to the meat. There are 4 ways to interpret a balanced chemical equation, so please make sure you're taking notes on each one of these different types. So first, and the one that you're probably most familiar with, is we can talk about a chemical equation in terms of particles. So an element is made of atoms, duh, we know that. A molecular compound is made up of only nonmetals, is made up of molecules, we know this. An ionic compound is made up of metals and nonmetals, and they're made of formula units. We also know this already, hopefully. So when we go to read a chemical equation, the way that we would read this one up here in particular is that we would say that we have 2 molecules of hydrogen and 1 molecule of oxygen form or produce 2 molecules of water. So again, we're using this word molecule, and we're just talking about those individual particles. So another example that we could have here is, the PowerPoint went a little crazy down there, so I'm just scratching it out, so don't pay attention to that. But what I do want you to pay attention to here is our example. So here we have aluminum oxide, and so remember, aluminum oxide is a ionic compound, so we're going to say we'd have 2 formula units of aluminum oxide produce 4 atoms of aluminum and 3 molecules of oxygen. So that's how we would read this one. Take a second and in your head just kind of think about how we would read this next example down here, this one right here. So I'm hoping that you're saying something like 2 sodium atoms and 2 molecules of water react to produce 2 formula units of sodium hydroxide. So hopefully that's what you're looking for. And hydrogen, sorry, in a molecule of hydrogen, this was hidden down here. A second way, and probably what for you is a new way to think about how to read a chemical equation is in terms of moles. So these coefficients can also tell us how many moles of each substance are needed. So the way that we're going to read this formula now is we might say that 2 moles of aluminum oxide produce 4 moles of aluminum and 3 moles of oxygen. So now instead of using these coefficients as referring to molecules or formula units, we're referring to them as moles. These coefficients are telling us how many moles we're going to need. And remember, moles is that measurement for counting the number of items, and it means 6.02 times 10 to the 23rd. So the way that we would read this next equation is that 2 moles of sodium along with 2 moles of water produce 2 moles of sodium hydroxide and 1 mole of hydrogen gas. So just a reminder that a balanced equation is a molar ratio. So we're going to use this thing called a mole ratio or molar ratio when we're doing these calculations in the next unit, or sorry, in the next video. So the third way that we can use chemical equations is in terms of mass. So remember the law of conservation of mass. We talked really specifically about this when we were balancing chemical equations. We said that matter cannot be created or destroyed. So in a chemical reaction, your starting mass needs to be equivalent to your final mass. And we can do that like using some more math, and I'll show you this on the next slide. So here's our chemical formula we're going to look at. We have 2 moles of hydrogen, 1 mole of oxygen. They are reacting to produce 2 moles of water. So let's just go ahead and compare the mass on the reactant side as well as on the product side, just to see that this is true. Okay, so here on the slide we're just going to show that the mass of the reactants is the same as the mass of the products in regards to the law of conservation of mass. So here I just did some simple conversions where I took our 2 moles of hydrogen, so notice our coefficient here is 2, so that's how I know that there's 2 moles of hydrogen. Then I just multiplied it by the molar mass, which is 2 grams for H2 because it's 2 hydrogens there. And then I came up with 4 grams. I did the same thing for oxygen. I know there's no 1 here, but remember there's that imaginary, so there's 1 mole of oxygen. You multiply it by 32. Again, it's O2, so it's 16 times 2, so that makes that 32. And then if you were to add these two things up, you would notice that they are equal to 36 grams. But then we can take our products. We had 2 moles of water, again the 2 coefficient here, and I multiplied it by the molar mass of water, which is 18 grams because it's 2 plus 16. And again, notice that this also gave us 36, so these values are the same, so the law of conservation of mass also applies. So the final way that you can interpret a chemical equation is in terms of volume. So at STP, and remember STP stands for standard temperature and pressure, and the standard temperature is 0 degrees Celsius, also known as 273 Kelvin, and the standard pressure is 1 atmosphere. you basically have 1 mole of any gas is equal to 22.4 liters. So when we look at this equation here, we would say that we have 2 moles of hydrogen, so we take 2 moles, okay, so 1 mole, but we have 2 in this case, times 22.4 liters. And then if we have oxygen here, we have 1 times 22.4 liters. And then this is going to produce 2 times 22.4 liters of water. Now, what you might notice is on this side we have 67.2 liters of reactant, and on this side we have 44.8 liters of product. So this is super important. The only thing that's conserved or the same on both sides of the chemical equation is mass and atoms. So the number of molecules might be different, or formula units, as well as the volume. We also include moles, will not necessarily be conserved. So mass and atoms are always conserved, however molecules, formula units, moles, and volumes will not necessarily be conserved, or the same on both sides.